Okay, let's dive right into this explainer on the giant demolition derby that is shaping our restless Earth. And to kick things off, we're going to look at a geological mystery that absolutely baffled scientists for over 150 years. I mean, when early explorers first started measuring the highest peaks of the natural world, they hit a puzzle that seemed, well, basically impossible to solve. Here's the puzzle. How in the world did deep-sea marine fossils and limestone end up at the very top of the Himalayas? We are talking thousands of meters above sea level. For a long time, people actually thought the measurements just had to be wrong. Limestone is a sedimentary rock. It forms underwater. So how does the literal bottom of the ocean end up forming the highest mountain peaks on our planet? Well, to solve this mystery, we actually have to look deep, deep underground. Because to understand our restless crust, we first have to recognize the massive engine churning underneath us. We're talking about convection currents. Deep within the Earth's mantle, intense heat causes these constant, rolling movements in the molten rock. Think of it like a giant, continuous driving engine that forces all of our crustal plate tectonic shifts. Without these incredibly powerful currents, our planet's surface would just be totally static. They're the invisible hand pushing the puzzle pieces of our Earth around.
Section 1. The Restless Earth and Divergent Boundaries.
So let's look at the first major type of movement in this giant planetary demolition derby. This is actually where brand new land is born. At a divergent boundary, tectonic plates are literally pulled apart by those convection currents we just mentioned. As the crust cracks open, magma rises up from below. Over time, this constant separating leads to seafloor spreading, massive rift valleys, and eventually the creation of mid-oceanic ridges. And you really have to wrap your head around the scale here. 70,000 kilometers. That is the sheer length of the mid-oceanic ridges wrapping around our globe. It makes them one of the most continuous and massive landforms on our entire planet. There's this continuous, expanding scar, creating new crust just hidden right beneath the ocean waves. Now, not all plates pull apart at the same speed. It's basically a geological drag race. The Mid-Atlantic Ridge, it diverges at a relatively slow, creeping pace of about 1 to 2 centimeters per year. But over in the Pacific, the East Pacific Rise, which is also known as the Chilean Rise, is ripping apart at a blistering 10 to 15 centimeters per year. In geological terms, that is unbelievably fast. Section 2. Friction and faults transform boundaries. So what happens when plates don't pull apart, but instead they grind side by side? You get a transform boundary, sometimes called a conservative margin. This is a fault line where plates move parallel to each other. Now, they might be moving in opposite directions or even the same direction, but at different speeds. The key takeaway here is they are neither creating nor destroying crust, hence the word conservative. But listen, because these are kilometer-thick slabs of solid rock, the movement is never, ever smooth. They snag on each other, and they build immense, terrifying friction. The San Andreas Fault is your textbook example of this. If you live in California, or honestly, if you've ever seen a Hollywood disaster movie, you know exactly what happens when those stuck plates finally overcome that friction. They violently snap past each other, releasing all that built-up energy as massive, shallow earthquakes. It is a very real, very powerful reminder of the incredible energy locked just beneath our feet. Section 3. The Subduction Zone. Convergent boundaries. This brings us to where plates don't just slide or pull apart, they violently collide head-on. And when two plates meet, their composition matters entirely. Dense, heavy basaltic oceanic crust easily sinks or subducts when it meets another plate. But continental crust? Completely different story. It's lighter and thicker. It's buoyant. So instead of sinking smoothly into the mantle, it tends to crumple, compress, and literally fold upwards into massive mountain ranges. And there's a really fascinating process that happens during these collisions. Imagine putting a thick layer of foam on the back of your hand, and then sliding that hand underneath a table. What happens? Well, the foam violently scrapes off and piles up against the edge of the table, right? When an oceanic crust subducts under a continental plate, the surface sediments are scraped off the sinking crust exactly like that foam. These scraped-off sediments accumulate, they pile up, and eventually emerge above the water as an accretionary arc. The islands of Japan are actually a perfect example of this exact phenomenon.
Section 4. The Ring of Fire.
Because the vast Pacific Plate is undergoing subduction on almost all of its sides, it creates a massive ring of geological chaos.
I mean, just look at it. From the Aleutian Islands and the highly active Kamchatka Peninsula, down through the Kuril Islands, Japan, the Philippines with Mount Pinatubo, the incredibly violent Tonga Islands, all the way over to the Andes Mountains in South America. This entire boundary is just a constant hotbed of global seismicity and explosive volcanoes.
Section 5. India's Epic Journey.
Okay, this is the monumental collision that is finally going to solve our opening mystery. Let's track this incredible chronological journey. Between 150 and 120 million years ago, the Indian plate broke off from the ancient supercontinent Gondwanaland. And as it drifted north, it passed right over the reunion hotspots, which essentially pumped magma underneath the plate, acting as a geological lubricant for its northward sprint. Ahead of it, the ancient Tethys seafloor was forced to subduct under Eurasia, eventually leading to India smashing directly into the Eurasian continental plate. Now, the crucial point here is this speed, 15 to 20 centimeters per year. I really want to emphasize this number because, in geological terms, the Indian plate was moving at absolute speeding ticket velocities. For a giant landmass, that is just ridiculously fast. We are talking about one of the fastest tectonic plate movements our planet has ever seen. And because of this massive speed, we get a completely unique chain of events. The incredibly fast Indian plate was relentlessly pushing the Tethys seafloor ahead of it. But the subduction rate couldn't keep up with India's speed. It was like a geological traffic jam. The seafloor experienced massive resistance. Because it couldn't sink fast enough, that ancient sedimentary seafloor brutally crumpled and got thrust violently upwards as the Indian plate barreled right into it.
Section 6. Forging the Himalayas.
The aftermath of this great collision was an unbelievable display of both destruction and creation. The epic resistance of the crash caused the weaker edges of the Indian plate to literally snap and sink underwater, creating the incredibly steep walls of the Western Ghats that we see in India today. Meanwhile, the intense head-on compression folded the continental landmasses into the mighty Himalayas. And right here is the answer to our 150-year-old mystery. The igneous core of these mountains was covered by the uplifted, folded Tethys seafloor sediments. Those marine fossils are sitting at the peak of the Himalayas because the ancient seafloor was quite literally pushed into the sky. Incredible, right? But here's the thing. The unstoppable power of our dynamic planet is still at work. Even today, right now as we speak, the Indian plate is still pushing north at 1 to 2 centimeters a year, which means the Himalayas are actually still growing by about 2 centimeters every 50 years. With these massive, heat-driven engines continuously churning miles beneath your feet, it really leaves us with one profound question. What will our restless Earth look like next?